Hey everyone. What's up? Welcome back to Chemistry Education Academy. Your go-to spot for mastering chemistry the smart way. If you've been following the series, you already watched our previous video on matter, its states, phase changes and classification. That video basically laid the foundation. Like the base layer of a cake, you know. Now today we're leveling up, we're diving into a super interesting concept that often confuses students but is actually pretty cool once you get it. Today's topic is allotropic forms of substances. So grab your notebook, stay focused, and let's break it down step by step. What is allotropy? Alright, let's start simple. Allotropy refers to the ability of a single element to exist in two or more different forms in the same physical state. Yeah, I know that sounded a bit textbookish, let me simplify it. Basically, same element, same state, but different structures, and because of that different properties. Kinda like how the same person can act differently in different situations, same identity, different behavior. Why do allotropes exist? Now you might be thinking, why does this even happen? Good question. Allotropy exists because atoms of an element can arrange themselves in different ways, and guess what? Structure changes, then properties also change. So even though the chemical composition is the same, the arrangement of atoms makes all the difference. Types of allotropy. Now let's break this down into two main types. 1. Structural allotropy. 2. Crystalline allotropy. Structural allotropy. This happens when atoms are connected in different patterns or structures. The best example: carbon. Carbon is literally the king of allotropy. Let's look at its major forms. Diamond. Each carbon atom is bonded to 4 other carbon atoms. Forms a 3D rigid structure. Extremely hard. Like one of the hardest substances known. That's why diamonds are used in cutting tools. Not just jewelry. Graphite. Each carbon atom bonds with 3 others. Forms layers. Layers slide over each other easily. That's why graphite feels soft and is used in pencils. Fullerenes. Carbon atoms arranged in hollow shapes like spheres or tubes. Example: C6 looks like a soccer ball. These are used in nanotechnology and advanced materials. 2. Crystalline allotropy. Now let's talk about crystalline forms. This refers to elements that exist in different crystal structures. A classic example: sulfur. Sulfur allotropes. Sulfur exists in multiple forms, but the main ones are rhombic sulfur, stable at room temperature. Yellow crystals. Monoclinic sulfur. Stable at higher temperatures. Needle-shaped crystals. Another important example: oxygen. Yeah, oxygen also shows allotropy. Oxygen O2. The oxygen we breathe. Colorless, odorless gas. Ozone O3. Made of 3 oxygen atoms. Has a sharp smell. Protects us from UV radiation. Ozone layer equals lifesaver. Why is allotropy important? Alright, let's get real for a second. Why should you even care about this topic? Here's why. Different allotropes equals different uses. Diamond used in cutting tools, jewelry. Graphite used in pencils, lubricants. Ozone is a atmospheric protection. Fullerenes used in nanotech. Medicine. So this isn't just theory, it's practical stuff. Common mistake students make. A lot of students confuse allotropy with isomerism. Let me clear that up real quick. Allotropy is showing by elements. Isomerism is showing by compounds. Don't mix them up in exams, that's a classic trap. Alright guys, that's a wrap for today's lecture. If this video helped you understand allotropy better, make sure you like the video, drop a comment if you have questions. Subscribe to Chemistry Education Academy. And don't forget, chemistry isn't hard, it's just about understanding the concept the right way. I'll catch you in the next video. Until then, stay curious, keep learning, and peace out.